Okay. Students, faculty members in the back, please be seated. Okay. So the first portion of the afternoon session will be an invited talk. My name is Janet Raveda. I'm a Center for Semiconductor Manufacturing Fellow. I'm also a professor at the Electrical Computer Engineering Department and have a joint appointment at Biomedical Engineering. Today, I'm very excited to introduce Professor Ali Javey as our invited speaker. Professor Javey is the Lam Research Distinguished Chair in Semiconductor Processing and a Professor of Electrical Engineering and Computer Sciences at the UC Berkeley. He's also a senior faculty scientist at the Lawrence Berkeley National Lab, where he serves as the program leader of Electronic Material, EMAT. He's a co-director of Berkeley Sensor and Actuator Center, BSEC. Professor Javey received a PhD degree in chemistry from Stanford University and was a junior fellow of the Harvard Society of Fellows from 2005 to 2006 before he joined faculty at the UC Berkeley. His research interest encompasses the field of chemistry, material science, and electrical engineering, and focused on the integration of nanoscale electronic materials for various of technology and applications, including low-power electronics, flexible circuits and sensors, and energy generation and harvesting. Professor Javey is an IEEE Fellow and a recipient of numerous awards, including the Dan Maiden Prize in Nanoscience Research, the MRS Outstanding Young Investigator Award, the Nano Letters Young Investigator Lectureship, the National Academy of Science Award for Initiatives in Research, Alfred P. Sloan Fellow, and the IEEE Nanotechnology Earlier Career Award, Technology Review TR35, and National Science Foundation Earlier Career Award. Let's welcome Professor Javey.
Well, thank you very much for the kind introduction. Thank you for organizing this event, for inviting me. What a great workshop, wonderful speakers, but what a great place. I had never seen a lecture hall like this. All right, so I'm going to try to use my time to share with you my thoughts about 2D semiconductors. In my lab, we have been working on 2D materials for over 10 years now. So I will try to tell you what we have learned in those 10 years, what I feel are the challenges, what I feel are the opportunities, and what I feel might be potential usages or applications. So as part of the talk, I will try to go from basic science to technology. Everything that I'm going to present to you was done by my students and postdocs, not by me. And so really the credit goes to them. So here I'm just listing a subset of students and postdocs who contributed over the last many years, specifically on topics related to what I'm going to present to you today. Also the funding agencies and a network of collaborators that we have been working with closely. All right, so I think in the morning session, the panel discussion nicely laid out the background for my talk, but I'm going to kind of restate some of the highlights. I'm going to start by showing transistor evolution. We, of course, started with planar transistors where the scaling was largely driven by gate oxide scaling. And then we moved to FinFET technology, which came out of Berkeley. And in this case now, we have a new knob where the scaling is driven not only by the gate oxide scaling, but also by the silicon thickness scaling, or the fin thickness scaling. And so now, from there, we have now moved to the gate-all-around devices, which you have already heard about, both nanowires and nanosheets. And again, here, the scaling is largely driven still by gate oxide and silicon thickness scaling. Now, the title of this workshop is 1D and 2D. Frankly, today's transistors are already 1D and 2D. And either in the form of silicon nanowires or silicon nanosheets, they're not 1D and 2D from quantum confinement point of view. Silicon has a very, very small Bohr radius, so quantum confinement doesn't come into place. You don't get 2D or 1D density of states. But from the microstructure or nanostructure point of view, these devices, today's devices, or at least near-term future devices, are already 1D and 2D. And so a expected evolution of this, I'm going to skip the CFET design, which I see simply as a derivative of the gate-all-around technology. An evolution of today's devices would be to scale the nanowires to the ultimate thickness, and there the thinnest or the smallest material that we have in the form of a wire is carbon nanotube. So that's why at least some member companies and researchers in this room believe that CNT FETs have a potential just because of their structure and properties that comes about. And also in the case of nanosheets, the ultimate scaling would be in the form of a semiconductor that is just a monolayer in thickness. And so that's where potentially some of these monolayer semiconductors could come into play. Now, I wrote down tomorrow's FET with a big question mark. I perhaps should have made the question mark even bigger. And that's basically yet to be seen. FinFETs took more than 10 years to adopt from the time that they were invented to the time that they went into production. Gate-all-around took over about 24 years from the time that they were first conceptualized and invented to the time that they went into production. So we will see how long it takes, if ever, for some of these emerging materials to be put in use. Now, if I start by looking at the nanosheet transistor structure, just looking at one layer, so you have a dual gate, top and bottom, and if I start to look at this device scaling beyond 5 nanometer gate lengths, then a number of problems arise. And one, of course, is that the electrostatics of this system starts to suffer. The drain capacitance starts to compete heavily with the gate capacitance. But also, direct source to drain tunneling becomes a major problem. And this is carriers directly tunneling through the barrier. And so to overcome these problems, if you want to push beyond 5 nanometer, first of all, you need a semiconductor that is super thin, just from electrostatics point of view. And it has to be atomically thin with no roughness. You need to have a low in-plane dielectric constant for the semiconductor, lower than what we have in silicon, to reduce, again, the effect of drain controlling the source potential. And finally, ideally, we need to have higher effective mass and larger band gap for our semiconductor compared to silicon. So we need a new material if we want to think about beyond 5 nanometer gate lengths. And I think that's perhaps where 2D materials, a lot of us believe that's where 2D materials can come into play. There is a large library of 2D materials, and here I'm just showing a small subset of some of these monolayer semiconductors. They all have different band gaps, they have different band alignments, And I think from maturity point of view, probably the two that are most promising would be tungsten diselenide. This would be the ideal material for PFETs, and moly sulfide. This would be the ideal material for NFETs. Now, if you compare moly sulfide specifically against silicon, you can't beat the thickness scaling limits. These are materials that have no dangling bonds. Of course, defects exist. And you can make materials that are a monolayer with atomic scale uniformity. Effective mass for MOS2 is significantly higher compared to silicon. The band gap is significantly higher. The band gap of 1.85 is vastly underestimated. There is a large exciton binding energy. The actual band gap, transport band gap, is over 2 electron volt. And of course, lower, significantly lower in-plane dielectric constant. And so we started looking at doing some simple simulation, just looking at the source drain leakage current for different transistor technologies. And specifically, we looked at both silicon and MOS2. And for the case of silicon, we looked at the 2 nanometer thick silicon and 1 nanometer thick silicon. And you can see that 2 nanometer thick silicon, the leakage current that you get, this is purely from just the source drain tunneling, is already too high even for 5 nanometer gate length. And in the case of 1 nanometer, of course, there's a big improvement, but still the currents are too high. Now, if you move to MOS2, in this case 1.3 nanometer, which would be bilayer, you can see that for a material that is a little bit thicker than silicon, you already get about 100x improvement in leakage current. And that's not because of thickness, that's purely because of effective mass and the in-plane dielectric constant. And of course, if you move to a monolayer, then there is a couple of orders of magnitude more reduction in the leakage current. So that's where the motivation for using some of these 2D materials comes about. Now, around that time, we wanted to validate these models. We were just doing simple simulations, and the question was, how accurate are these simulations? Can we think about experimentally fabricating transistors with gate lengths that are sub 5 nanometer, and how do we do so in an academic lab, just as a proof of concept? At the time, we really didn't know how to make a 1 nanometer line, metal line, so we just decided to use carbon nanotube. So this is a this goes very well with the topic of the workshop, 1D and 2D. So we use nanotube as a gate. And in this case, the device has just a single gate. You don't have a dual gate structure. It's just a single gate, just a simple proof of concept. We have source and drain, and then there are these large underlap regions which are electrostatically doped by a separate gate voltage. Now, in this device from the TCAT simulations, we see that the effective channel length in the off state is 3.9 nanometer for a 1 nanometer physical gate length. So the gate length, think about it as sub 4 nanometers. So the question was, can you even turn off this device? Electrostatically, can you turn off this device with a physical gate length of 1 nanometer? And so these are the IV characteristics that we got. We were able to get about 65 millivolt per decade subtertial swing. And these are pretty good transistors, granted that the current levels are very low. And the current levels are very low because the contacts and also those extension regions that we have that were just simply acting as big parasitic resistors. So as a proof of concept, this shows that you can, in principle, make devices with physical gate lengths sub 4 nanometers, sub 5 nanometers, using these 2D semiconductors. Now, to just highlight the sensitivity on the thickness, we looked at, we built different devices with different moly sulfide thicknesses. So 1.3 nanometers, that would be bilayer, that's what is shown here. 12 nanometers, that's the red one, and the blue one is 31 nanometer. So if moly sulfide is 31 nanometers thick, there is no current modulation by the gate. You have a perfect resistor. And even for the case of 12 nanometer, you can still have a good gate modulation. Granted, the substrate swing is worse. All right, now this was just a simple proof of concept demonstration, and it's definitely not a manufacturable device, the architecture that I presented. A manufacturable device, which we have heard earlier today, will be in the form of a nanosheet configuration, most likely, with gate on top and bottom. And so the structure would look something like this, at least for just looking at one nanosheet. So here I highlighted some of the challenges, and the slides were already made, but after the morning panel discussion section, you can actually see that what I consider to be the challenges is also what others in the community feel are the fundamental challenges. So let me just highlight a few. The first is growth. There are, of course, people that believe that transfer is a viable process, and it may indeed be a viable process. We will see. But direct growth is often the best, especially when you're talking about yield and cost. So if you can do direct growth, there is no doubt that that would be the way to go. Now, if you want to do direct growth, you need to have a low temperature process. You need to be able to get low defect densities. I genuinely believe you need to have single crystalline patterns. The orientation of all the sheets need to be well aligned. And the reason why the orientation needs to be well aligned is not because of mobility, not because one has a higher mobility than the other, but because of the edge states. Depending on the orientation, you will have different edge states, the edge states. Some are metallic. And this is really problematic, especially when you make the sheets very narrow. Contacts. I don't need to talk about contacts. I think we have talked about a lot of the issues, but I will highlight it even more in the next few slides. Gates. How do you put down a gate dielectric when the surface has no dangling bonds, when the surface has no chemically active bonds? For the edge states, we have to think about how we can passivate them. At the edges, we have a lot of the dangling bonds, and of course, inline metrology using contactless optical or electrical characterization methods. Now, for the purpose of this talk, I'm just going to highlight one problem, which is something that we are actively working on in my lab now, which is developing contacts that are fab-friendly, contact processes and materials that are fab-friendly, and at the same time getting also, of course, low contact resistances. I think the optimal device structure perhaps will be what is shown here and here, where you have a dual gate, you have the contacts, whatever material you use, whatever metal you use, maybe they're raised contacts as well, but then you have these heavily doped extensions. So this is very much like how we make our conventional MOSFETs. You need these heavily doped extensions to reduce your contact resistance. This is how we have been classically overcoming the contact resistance problem in silicon. The heavier the doping concentration, the thinner the barrier heights, the thinner the Schottky barriers at the interface, and the more tunneling, the higher the tunneling probability. So the key is to dope these ends, but dope them very, very heavily. Now, you can think about how to dope, and there are different doping schemes. You can do substitutional doping, for example, which was highlighted earlier today. But I think the most promising approach for doping 3D materials is remote doping. And remote doping is a concept that we're all familiar with. If you have a slab of silicon, just a silicon wafer, and in this case I just wrote it as being p-type, I can draw the energy band diagram going from top to the bottom. So here is the air or insulator on top, and this is the semiconductor that is uniformly doped. I can do the same thing for my monolayer, draw the energy band diagram from top to the bottom. This is what you get. Now what I can do is place a sheet of charge, fixed charge, somewhere close to the semiconductor. And if you do so, if you can somehow put a slab of charge, fixed charge, in close proximity to your conventional silicon, of course, you end up getting energy band bending. And this is how, of course, a MOS capacitor works. The slab of charge is created by a gate. But this concept is also can be used for VT control, the threshold voltage control. And this concept is also used in most commercial silicon solar cells. In silicon solar cells, they create surface band bending by putting, for example, insulators with fixed charges in them in order to repel the minority carriers from the surface. But in the case of a monolayer, there is no depletion. There is no depletion depth. There is going to be no band bending going from top to the bottom. You cannot drop potential across the thickness of the semiconductor. So the bands will be flat if it's just a monolayer. If it's a bilayer, you can start to get some band bending, and as you add more and more layers, you will then get closer and closer to the left. So while in this case, some of the positive charges that are placed on the surface are compensated by the depletion charges of the semiconductor, and you can keep depleting it more and more, over here, whatever fixed charges you put on the top will be compensated by the electrons or holes that you will bring in by the inversion charges or accumulation charges in your semiconductor. So this is a very promising approach for materials that are fully depleted, or in this case, materials that are at the thickness scaling limit, where there is no depletion, there's no depletion depth. The entire structure is, the depletion width is just limited by the thickness of the material. So the question is, how do you do remote doping? And the very first works that we did in this field, looking at the 2D devices, going back to over 10 years ago, was looking at doping, and specifically doping in the context of contacts. And in fact, at the time, the only semiconductor that was known, the only monolayer semiconductor that was shown to have high mobility was molybdenum disulfide. People had tried to make tungsten diselenide monolayer devices. The mobility was very low. And there were theoretical studies being done to understand why the mobility of tungsten selenide is low and moly sulfide is high. It had nothing to do with mobility. It had to do all with contacts. The mobilities were not extracted correctly. The contacts were shuckly for tungsten selenide. So once we were able to dope the semiconductors heavily, we were able to form better contacts, and we were able to get high mobilities with tungsten selenide. So let me show you the different schemes of doping using remote doping. One is to simply put down a nitride layer that has a lot of fixed charges. Nitrides are well established to have fixed charges. You can control the fixed charge density by the plasma conditions. It's a well-established field. And you can control the doping concentration by controlling the fixed charge density. Now, there are problems with this. Nitrides, the fixed charge density does not linearly scale with the thickness of the nitride. You need a minimum thickness before you start to see some of these effects. And so it may not be very scalable, but you can use materials like aluminum oxide, which are well established to also have fixed charges. Another approach to do remote doping is to use surface charge transfer. In the case of surface charge transfer, you use species, whether it's thin films of materials like oxides, or molecules, or even atoms that are either electron withdrawing or electron donating. Basically, materials that have very different work functions compared to your semiconductor. If you have a very different work function, there will be charge transfer. When that happens, you will have charge separation. You will have basically fixed charges on top, and the semiconductor will then be effectively doped. Another method would be to do covalent functionalization, and in this case, we looked at forming oxynitrides, and you could just do plasma reaction or low temperature reaction with NO2, and you can form oxynitride. And what happens is you form tungsten oxynitride on the surface, and tungsten oxynitride has a high work function, so that's how you get surface charge transfer. So this is just a library of different doping techniques. Now, frankly, the best one for getting large electron concentrations is using potassium. Back then, we were doing 10 years ago, we didn't care about CMOS compatibility. It was all about proof of concept. You get very high concentration of potassium, which is CMOS incompatible in every way. It goes everywhere. Its air stability is a problem. But potassium, what happens is you put it on the surface, so this is remote doping, and it donates an electron to the semiconductor underneath. You form potassium plus. So what we are doing in my lab now is borrowing these concepts but coming up with CMOS compatible processes. And I think that's really the key, not just to form doping, high doping concentrations, but it has to be CMOS compatible. All right, so that's all I'm going to say for the scale transistors. The next topic that I'm going to cover is monolithic 3D integration. And I think we heard earlier this morning, great presentation, highlighting how monolithic 3D integration is very promising with these 2D materials. It's already proven to work well using transfer processes, but ideally, again, you want to be able to develop low temperature growth. And in the case of monolithic 3D integration, this is an old cartoon. I actually grabbed this from a talk that I had given 20 years ago. And I still had the slides. And I decided to stick with it, even though transistor structures have changed quite a bit. But monolithic 3D integration is an old topic. It goes back to 30 years. And to this day, we still talk about it, but we haven't been able to get close to it in terms of realization. So let me show you some of the work that we did on the 3D stacking of 2D materials. And here we use transfer process. Again, the question is it a manufacturable way or not? You can decide, but that's the process that we used as a proof of concept. So the idea here that we used was if you have a single layer CMOS, you have your NFET and PFET side by side, but you can start to, of course, stack one layer on top of the other. For example, you can stack the PMOS on top of the NMOS. Depending on what you're building, you can also share the gate, of course, between the two layers. And so this in some ways is similar to the concept of CFET that is being proposed beyond the current gate-all-around structure. And so using this approach, we built different digital circuits. This would be this is how the layout looks for the different digital circuits that we built. If they were single layer, when we built them double layer, you basically, the way you can think about it is you fold it along this dashed line and you put the PMOS on top of the NMOS. You get about 40 to 50% area reduction by using this approach, depending on what logic you build, what circuit you build. So these were some of the results from our earlier work. And you can see that we built devices. The way we did the fabrication was we first built devices on moly sulfide. So that's our NMOS. And then we built the PMOS on top. And from the TM images, you can see where the PMOS layer is, the tungsten selenide, and the NMOS layer, which is moly sulfide. Now, using this approach, you can, of course, also build a library of other circuits, including analog circuits. We use the same approach and the same process. We also build 3D analog circuits, and here I'm just highlighting a few of them. Now, when it comes down to the 3D integration approaches, the thinking here is you will have, of course, the bottom layer as logic, and on top of it, you stack memory or analog. And I kind of highlighted how we can put the analog on top. And then moving to the top layers, you can also stack various sensors or optical input-output devices, photonic devices. And we heard from Todd this morning that photonic devices is an area of emerging need. And so then the question for us was, if we have a process that we can grow or transfer these materials reliably in a heterogeneous manner, in a monolithic manner, can we use the same materials with, of course, a different device structure as photonic components? Can we use these monolayers also as photonic devices without having to change the platform? And so we started looking at this problem about a decade ago, and the question was, are these materials good as light sources? Can we use them as light sources on our silicon chips? So the starting measurement that you do always when you're trying to build light-emitting devices is you do photoluminescence quantum yield measurements. And the maximum device efficiency, if you build the LED, will be your quantum yield minus all the other non-idealities that come about when you build a device. So when we looked at moly sulfide as processed, the quantum yield we saw was extremely poor, less than 1%. So if you build the LED, it will be less than 1%. We looked at this, and we looked at various approaches to improve the quantum yield, and what we found was treating the monolayer with this molecule, and this molecule is called TFSI. It's a Lewis acid. It dramatically enhances the quantum yield to about 100% at low generation rates. So think about generation rates as the brightness level of the device, how many excited particles you're dealing with, how many, of course, what we really care about is operating the devices over here. But nevertheless, in the low regime, the low excitation regime, we saw that the quantum yield was high. So then the question was, what's the mechanism for TFSI enhancing the quantum yield? We knew that TFSI is a Lewis acid. Lewis acids are molecules that withdraw electrons. So this goes back to the charge transfer. So to validate the mechanism, we built devices where we were doing gated photoluminescence studies. So we were measuring photoluminescence of a monolayer while applying a gate voltage. And you can clearly see that the photoluminescence strongly depends on the gate voltage. When the gate voltage is 0, just like a as-made flake, this is for moly sulfide, the quantum yield is very, very low. The brightness is very low. You can see that the normalized spectrum is still there, but it's just very dim. When we apply a negative gate voltage, the material literally glows. It becomes very, very bright. And so by doing quantitative measurements, we can measure the photoluminescence quantum yield as a function of generation rate for different gate voltages. Now, when you're thinking about these gate voltages, the substrate was a very thick oxide for these measurements. You have to think about where the Fermi level is. In the case of moly sulfide, as made, as processed, the material is known to be N-type because of the native defects, and the Fermi level is close to the conduction band. If you apply a positive gate voltage, the Fermi level moves further close to conduction band. If you apply a negative voltage, you can move it to mid-gap. And so based on the data that we got, we were able to come up with a very simple model. In the case of these monolayer semiconductors, they're excitonic. They're excitonic systems, just like quantum dots. And we know quantum dots are bright. There was a Nobel Prize given to quantum dot for their brightness, even though they're super tiny with a lot of dangling bonds. And here it's also excitonic, and the excited state has two different formal particles. One is a neutral exciton. A neutral exciton is simply a bound state of an electron-hole pair. And then the other one is a charged trion, basically two electrons and a hole, or two holes and an electron, so it can be negatively charged or positively charged, being bound together. So this is how the excitonic systems look. Now, in a free carrier system, if you have any defects, the free carriers will non-radiatively combine with the defects. In an excitonic system, the excitons, the only way they can interact with the defect is for them to split. And once they split, then they can undergo Shockley-Reed-Hall, the SRH. But in the case of monolayers, the binding energy of exciton is on the order of 1 electron volt. It's very difficult to split these excitons. And so what we see is, if we can form our particles mainly in the form of neutral excitons, the material is purely bright. The process is purely radiative. And on the other hand, if we form charged trions, the process is mainly non-radiative. And this is expected because this looks like an OJ recombination. If you think about it, two electrons and holes, that's how OJ recombination looks. So we can make these materials bright if we can form neutral excitons as opposed to charged trion. And the way you can control the concentration of the two is by doping. If your semiconductor is intrinsic, the Fermi level is close to the mid-gap, you mostly have neutral excitons. If you are doped, either electron doped or hole doped, you have a large background charge, then you can form trions. So the gate is modulating the exciton to trion concentration ratio. Now, in the previous slides, I showed you that we can make the luminescence quantum yield very high at low generation rates, but the key is to get them to be high at high generation rates. When the generation rate is high, you have a lot of excitons. The exciton concentration, the material builds up. And when you have very high exciton concentration, now you can get exciton-exciton annihilation. One exciton can transfer its energy to another exciton. You form an excited exciton, and that thermalizes. So that's a non-radiative process. And what we have been able to show more recently is by applying strain, just the mechanical strain, by doing strain engineering, we can actually dramatically reduce the exciton-exciton annihilation so that the material is bright even at very high generation rates. So this slide summarizes what I just highlighted, that one way to look at the uniqueness of these 2D materials is to look at the maximum brightness that you can get versus defect density. And of course, gallium nitride can be very bright, but the tolerance to defects is very low. You have to have very low defect densities. In the case of 2D materials, despite having very high defects, very high defect densities, the processing is very naive. We have a lot of defects in these materials. We can get very bright materials. And I think that's really an advantageous property when you're thinking about integrating these things for monolithic 3D stacks where growth conditions are not going to be optimal for some of the 3-5 materials. All right. Now the next question is, can we somehow make electroluminescent devices? So if we have a monolayer, can we electrically pump it and have it as a light source on our chip? And we looked at different schemes, and we came up with this simple structure, which is a MOS capacitor that is being operated in the transient mode. Now, if you have a conventional bulk silicon MOSFET, if you apply a high voltage beyond the threshold voltage very quickly, you put the capacitor in deep depletion. So you don't bring in any inversion charges. That's deep depletion. But in the case of monolayers, there is no deep depletion. There is no depletion depth, which I talked about. So in this case, what happens when you flip the voltage really fast between the source and the gate, you can't undergo deep depletion. So the only place where the potential can get dropped at time 0 when you flip the voltage fast is right at the metal semiconductor junction. So you end up with getting very large energy band bendings at the metal semiconductor junction, and you get thinning of the Schottky barriers, and you get very rapid injection of charge. So let me show you how it's done. Let's look at the case where you're at steady state. The gate voltage is negative, and the energy band diagram between the metal to semiconductor looks like this. You flip the voltage, you look at the during the transient, right at time 0 when you flip the voltage, you get this. And you can see the quasi-Fermi levels, but look at the energy band diagram. The conduction band is below the Fermi level of the metal by 2.5 electron volts within the first 7 or 8 nanometers. The first time I saw this energy band diagram, I told my student, this is impossible. I said, you cannot have a conduction band being below the Fermi level of the metal by a couple of EVs within just a few nanometers. And he looked at me and said, yeah, you're right, it's impossible. Let me look at it again. And he looked at it again, and the answer is no, he's correct. It's just, it's transient. We never looked at, we typically don't look at the energy band diagram under non-equilibrium conditions. And so what ends up happening is that when the band bending is like this, electrons will very quickly tunnel through from the metal to the conduction band, and at the same time, of course, some of the holes will leave. You form excitons, light comes out. The light then stops, you reach steady state, you flip the voltage again, light comes out. So you can look at the electroluminescence, and we can get this pulse emission. And so we have a pulse light source, and we can control, of course, the frequency and the emission characteristic by controlling our pulses. One of our undergraduate students decided to grab this approach, and she did CVD grown. She looked at CVD grown tungsten sulfide, and tungsten sulfide, the band gap is red, is bright red, and so she optimized the CVD growth to get the highest possible quantum yield, and so this is now a centimeter scale chip. And she was able to, using this device architecture, to build these pixels. So we have an array of 4 by 4 pixels, and she was able to make a tiny display writing 3 randomly selected letters. And so I asked her, what's the brightness level of this device? Remember, your emitter is only a monolayer. I mean, just think about it. You have a monolayer in thickness. Can a monolayer emit too much light that is visible by eye? The analogy that she came up with was hot plates in the lab. Many hot plates have a red display, and she said the brightness level is equivalent to that. These images are taken under ambient lighting, and they're just taken by a phone. These are very bright devices indeed. All right, now I'm going to change the topic a little bit, but still maintaining the content on related to this heterogeneous integration or monolithic heterogeneous integration. And now I'm going to talk about another example of layered semiconductor, which is interesting. And this one is tellurium. Now, tellurium, the crystal structure is quite interesting. Tellurium is made of these molecular chains of just tellurium atoms. So these are 1D chains of tellurium. And they stack by van der Waals forces laterally and vertically. So you form layered materials. Now, what's unique about tellurium is you can evaporate it at cryogenic temperatures by just using thermal evaporation, but cool down the substrate. We cool down the substrate to about 100 Kelvin, 150 Kelvin. Then we evaporate. We bring the chip back to room temperature, and it crystallizes at room temperature. So these are the results that you get for thin films of tellurium evaporated on SiO2, crystallized at room temperature. And the grain sizes are on the order of tens of microns for a material that is crystallized at room temperature. And of course, you can do some structural engineering. You can template it. So if we template the tellurium, evaporated tellurium into smaller patterns, then we can get single crystals at each pattern. And so this is a mechanism by which you can form single crystalline arrays of tellurium structures on your oxide, all processed at room temperature. We have built different types of devices using tellurium. And specifically, here I'm showing you some of the PMOS devices that we have built. The mobility is, the effective mobility is about 30 centimeters squared per volt second. Which is you know, much lower than silicon, of course, but this mobility is pretty competitive if you think about oxides. And oxides, many oxides are being used as N-type devices. So this is a P-type device. This is analogous to oxides, but it's now for the PFET. Now, the other key feature is there is no mobility degradation at high fields. The mobility is constant. And again, that's because it's a layered structure, so you don't have any atomic scale roughness. Using this approach is pretty scalable. We can do wafer scale processing. So my student Chun-Sung built inverters, NAND, full adders, and 2-bit multipliers on a wafer scale, on a wafer, using this simple process. The yield, of course, is quite high. We have also used this for building 3D stacking, but this is 3D PMOS circuits. We didn't incorporate it with an N-type material, but in principle, you could do the same thing with an N-type oxide. And so we have 2 layers of transistors. You can build your tellurium transistor first, 1 layer, build a second layer on top. You can integrate them together. build different logic gates, and it works. Now, tellurium is also a good material for light absorption. In the bulk form, the band gap goes from 0.3 electron volt to about 1.9 electron volt if you alloy it with selenium. And this is the bulk form. If you reduce the thickness, then the quantum confinement effects is dramatic. You get also another degree of control in the band gap. And so we have started to use this, the tellurium devices, as our photodetector technology that we can readily fabricate on chip. And so here is an example device. I'm showing actually 3 different devices: selenium, tellurium, alloy with different concentrations. And I guess the key figure of merit would be the room temperature operation. Detectivity is on the order of 10 to the 11 for the 1 micron or so wavelength range, 1 to 1.5 micron wavelength range. It's pretty competitive given how low cost and simple of a processing scheme this is. The students were able to array these devices. They built arrays, in this case 42 by 42. They built imagers. Again, the yield is high, and we were able to do imaging, IR imaging, using tellurium. Tellurium photodetectors can be readily integrated with photonic chips. We collaborated with Yelena's group at Stanford, and we grabbed some of their photonic structures, the waveguides based on lithium niobate, nitride, and also SOI. And we grabbed their waveguides. We integrated our tellurium detectors, and it works, not surprisingly. And so here are some optical images, and here you're looking at an 8 by 8 array of detectors used on silicon nitride waveguides. These devices are also fast, and we were able to operate them up to 10 gigahertz, and without significant droop in the efficiency. So we have fast detectors. All right, now to wrap up the talk, I'm just going to briefly highlight one other wavelength range, which is mid-IR. So tellurium is good for going from a little bit beyond mid-IR, closer to the short wave. And the question is, can we make good mid-IR optoelectronics as well on our CMOS chips? Your camera, your phone today has near IR devices on it. It has a near IR light source and detector. It's used for facial recognition. So near IR detectors are already being implemented. If you can move to mid IR, you really open up a whole venue of capabilities, because there are many molecules. Most molecules have their fingerprints in the mid-IR regime. So you can start to look at chemical sensing. Now, a problem with mid-IR is that when the band gap of material is very small, the material typically suffers from efficiencies. And specifically, if you have a material in the mid-IR with the band gap of, let's say, 0.3 electron volt, the maximum efficiency that you can get from that material for light emission is about 0.1, at best 1%. Those are the commercial, state-of-the-art commercial LEDs in mid-IR. $300, tiny LED, 0.1 to 1% efficient. And the reason is, as you shrink the band gap, OJ recombination shoots up dramatically. And so you're purely limited by OJ recombination. If you have a material of similar band gap, but with more symmetric electron and hole masses, then the OJ recombination rate can be dramatically lowered. One material that is pretty attractive is black phosphorus. And this is a material that we have extensively looked at in the past couple of years. We can now make black phosphorus devices that are 20% efficient when integrated with the proper cavity. And these are materials that are very, very bright, and the devices are already better than what you can buy today. So here is a table of what you can buy today, and compared to black phosphorus. This is for a LED looking at the external quantum efficiency. Our BP device is at 4%, and the wavelength that it's emitting at is 3.6 micron. The only number that you see that is bigger, that it comes close to it is for gallium, indium arsenide, antimonide, but it's for a much shorter wavelength. It's for 2.3 micron. So you can see that we are already better than what the state-of-the-art can do. And so let me just go to the last slide. Scalability is a big issue, and we are now looking at various schemes of processing black phosphorus on scale. And so here we have a wafer with black phosphorus thin film on it. And so we have come up with ways of depositing these thin films while maintaining their brightness levels. So I think this is another area where 2D materials have a distinct advantage. The state-of-the-art is poor. Silicon MOSFETs are pretty darn good, but in mid-IR, the light sources are pretty poor. And the detectors as well, the detectors are very poor. So let me just come to the conclusion slide. I hope I was able to kind of give you a flavor of some of the work that we've been looking at, going from materials, fundamental material properties to devices. And there have been a lot of advancements in the field over the last 10 years by the community as a whole. But the key message is many challenges remain in contacts, doping, and high material growth. Transfer looks promising. Is it manufacturable? And if it's manufacturable, then many of the devices, certainly the photonic devices, can really be incorporated using the platforms that I talked about. All right, and so with that, thank you very much, and I can take questions that you might have. Thank you.
Are there any questions for Professor Javey?
Thank you very much. Great presentation, Umberto Solano from Arizona State University. Somewhere, well, in light of all the things that you showed in terms of quantum yield and how sensitive that is, back to the slide where you were suggesting we need contactless, large area fast metrology. How confident you are that we can get with any light-based metrology to a reliable estimate of defect densities, depending also what we define defect, but I think you get the question.
So you might remember this, but the way we started this project was we said photoluminescence quantum yield is very sensitive to defects, and can we use that as a metrology method to control the material quality for electronics? That's how the project started. And at the time, we had an NSF center and called E3S, and where we were worrying about band edge roughnesses and the defects, and that's how this project started. But over the years, we learned that the quantum yield is, unless your defect density is too high, that you're changing the band structure, and you can then start to easily split the excitons, or very quickly couple with a fixed charge in the material to form a trion effectively. Unless that's the case, what we found is photoluminescence quantum yield is very sensitive to doping and strain. So you can use it as a metrology method if you can charge the surface controllably. And there are, in principle, ways that you can charge the surface contactless, right? So you charge a surface, you measure quantum yield, you charge it again to a different value, you measure the so that's in principle possible, and you can get those plots that I showed, which is the quantum yield versus generation rate. You can easily collect those without having a gate, without having a voltage, by just simply electrostatically charging the surface by using different schemes, the contactless schemes. So if those schemes can be incorporated, then I think for sure, at least you can use this as a way of getting a sense of your strain distribution and also your doping profile.
Yes.
Thank you, Javey, for the great talk. My question about maybe a little bit general, stability of these material systems. So stability. So if you can make some give some thoughts on it, it will be greatly appreciated. Are they stable? If they're not stable, what could we do to make them more stable?
Very good. So I think collaborations with industry is very important. That's what we heard today over and over again. I really think that's important. A couple of years ago, a Japanese component manufacturer called Asbil came to us and they said, well, you have pretty good light sources in mid-IR. How stable are they? Can we design a project? And they funded us. They sent a VIF to our lab, and the VIF is Shogo-san listed here. And the question was, can we make LEDs, BP LEDs that are stable? And what's the stability? So black phosphorus is interesting. Black phosphorus, if you make it monolayer, and we try to measure the optical properties of monolayer, the material literally disappears while you're measuring it, even in vacuum. It's very unstable. So monolayer black phosphorus is useless. Bilayer is useless, very unstable. By the time you get to 10, 15 nanometer, the material becomes pretty stable. Now, the band gap also changes. The band gap that we care about is in mid-IR. We want the bulk band gap. We don't want to thin down the material. If you thin down the material, you go to near IR and visible, where there are better choices. So for black phosphorus, you want it to be in the bulk form. And one thing that we have measured in the films that are tens of nanometer thick, maybe more than 15 nanometer, the students measured the photoluminescence quantum yield. They grabbed the sample, they did oxygen plasma on it. So they put it in an oxygen plasma chamber. We did oxygen plasma, we destroyed the surface. And you look at AFM and the surface is rough, it's oxidized badly, damaged. We measured the quantum yield. The quantum yield did not change for that thickness range, right? And so that data is in one of our papers. The surface seems to be pretty inert for the case of black phosphorus. I think what's happening is you're oxidizing the surface, just like silicon forming silicon oxide, but that oxide seems to be layer by layer, and it seems to be self-limiting. So meaning once you form it, then you kind of isolate the passivate, self-passivate, the structure. Now, for the case of LEDs, what we did was we packaged them properly, and the way we did the packaging is what people had done for black phosphorus transistors before. And for transistors, I don't think black phosphorus makes sense just because the band gap is wrong. Unless you go to monolayer, but for monolayer, it's very, very unstable. And so for the black phosphorus, we just passivated with aluminum oxide. This is ALD oxide. And we then put it in a chip carrier, and we basically sealed it in epoxy. And then we measured the operation lifetime. So we continuously operated the device. So we were looking at a device being operated at a pretty high intensity. I forgot the intensity is in the paper, but it's higher intensity than what you can buy today for mid-IR LEDs. It's a high intensity, and we are running it for, you can see how many hours, over 100 hours. Here, it looks like it's noise, but our photodetector ran out of liquid nitrogen. You're talking about tens of hours, so we had to constantly fill the liquid nitrogen in the detector. So it's, yeah, so the devices are very stable. We did the half-lifetime measurements by doing the accelerated lifetime studies. That's what is being shown here. We operated devices at different temperatures, up to 140. We extracted activation energy. So the half-lifetime that we got at room temperature is 15,000 hours of continuous operation for these devices. So for the case of black phosphorus LEDs, they're actually very stable. And I didn't talk about the processing, but one of the processing techniques that we're using now is to make inks. So we can just grab black phosphorus, make an ink out of it, and the surface is pristine. The surface is inert, as I told you. We can just solution process the ink on the surface, and we can make very bright LEDs, mid-IR, because the state-of-the-art is so poor. So it's always easy to compete in an area where the state-of-the-art is poor. Yeah.
Thank you. Let's thank Professor Javey for his wonderful talk.
Thank you.